Okay, we should start. Cool. I hope you're ready to and excited to start a new semester. And um, so this is advanced cognitive modeling, as you likely know. Just as a note, I tend to stream and record all the lectures so that if you cannot come to lectures for whatever reason, you always have them accessible. If you want to look at stuff at a later point, you have it accessible. That means that uh, to a certain extent, your questions and comments will be recorded. I'm actually recording with this mic, which means that probably it won't record your questions. I'll have to repeat them. But just so you know that that's something that's going to happen. The lectures are not advertised anyway, but I put them on a YouTube channel so you can see the lectures of this year and of the previous years, and they stay there as a record. So you shouldn't feel shy because of that. Probably it's just going to be me uh, repeating the question anyway. Good. But more on that later. The first thing is most of you know me already a bit, but not everybody, I think. Have I already had all of you? Probably, right? At Social and Cultural Dynamics. Method 3. Yeah, that was the year. Yes. Okay, yes. There's been a few shifts. Yes. Cool. So, you know that already. I'm just going to say a few words. I never took a course in cognitive modeling. I never took a course in Method 3. I was trained as a semiotician, somebody who studies philosophy and then thinks very hard about how things make sense. And I was doing that in Italy, so we ended up spending a lot of time on books and wine and movies, and that was a very fun thing. But e- so now what I do is as I identify as a cognitive scientist, I mostly do computational and statistical methods, empirical, sometimes even experimental data. But that kind of approach of how we make sense together is still going to shine through also this course, right? So the way that I approach cognition is that it's a collective meaning making. Uh, it's something, the way that we process information, that way that we make decisions, even the way that we perceive the world are not something that, as would say, happens in the brain, period. It's something that is shaped by the ways in which we participate of society. I would not even be allowed to make an important decision without talking to my kids, to my partner, being shaped by the cultural tradition and so on and so forth. And it's trying to analyze these things that has brought me to cognitive modeling. Because as soon as we start to have these complex interdependencies between how I act in the world and that changes the stimuli that I receive, how I interact or search for informations from other, that changes also the information that gets given to me and the way that I process information, et cetera, et cetera. You start needing more complex tools than just a regression model. In particular, given that I was trained as a musician, then these models in themselves, these complex techniques, are for me like a cultural artifact that I can't keep on second guessing myself on. Like models are cultural artifacts that change the way we think. And that's also one of the ways that these courses structured, teaching you to think in certain ways through the use of computational cognitive modeling. And and as we do science, of course, I was trained as a humanist. Sucks to be me. I can't help just second guessing myself again and trying to think how the traditions of science in which participate, the courses that we take, the kind of statistics and tools that we have available shape the way we do science. And again, this is something that I won't try to put too much emphasis on, but it will shine through the course because that's the way I think. And I think that's one of the ways that the CogSci students are better than many other students because you're able to critically think about the tools that you use. This is just an ad, basically, that you're just starting with me, but I'm always looking for collaborating with master students in your thesis. When you choose your internships, I have a collaboration with the hospital, the psychiatric hospital, where we have every now and then people um, doing internships in topics like cognitive modeling of cognitive function relevant to psychiatric disorders. For instance, we work on executive function. Dysfunctions in your attention is something that's common across many diagnoses, let's say ADHD and bipolar disorder and psychotic disorders. But there is these strong beliefs in the medical communities that you cannot give methamphetamines to psychotic or bipolar patients because that would generate induce either psychotic episodes or manic episodes. And however, that's not always the case. Like there are projects that have been giving these drugs to these kind of patients. And now the question is that because there's heterogeneity in the way that attention is impacted in these patient populations? And if we can capture that with cognitive modeling, we could personalize the treatment. That's very far in the future, but can we actually meaningfully build models from what we know about cognitive science that tell us something more about why there is an attention deficit? What are the mechanisms involved? I also work a lot on conversations. How do we quantify conversations? How do we make models of how humans behave in conversations, especially in the field of autism and schizophrenia? Um, and I also work, as I was mentioning before, with this meta angle on science, on information flow in science. How do we understand the way that scientists spread their ideas? How do we understand the ways in which these ideas spread through papers and patents and stuff like that? Sorry for the ad, but I thought I would put it in front so you know that there's projects if you're interested in doing stuff, or there's a year open to listen to your ideas on those topics. So I want to do a quick round of names. Uh, since I had kids, I have lost any hope of actually remembering all the names, but I'm going to make an effort. We'll see. Could we just do a round of names, and then I'll probably have to ask you whenever you ask a question the first few weeks to repeat their name so that I can remember it. Yes. Mhm. Yeah. Sorry, can you repeat? Iskia. Okay. Yes. 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 Cool. I'll ask you again, but starting to put some anchors. So we'll start very much in the middle of the course. We'll start with a deep dive, and only then we will zoom out and talk about what we're going to learn throughout the course. So this is a very crucial problem in my life. This is a pizza oven. It's gas fired. Because if you want to bake proper pizza, it needs to be at the very least 400 degrees, and electric ovens cannot deal with that. Well, home electric ovens cannot deal with that. So, in order to engage my kids in me baking the pizza, because it should be a family activities, I bought this toy, which is a temperature gun, which allows you through infrared to measure the temperature inside the oven so you know when to bake your pizza. However, having kids, they want to play cards. And this game called Karak is their current obsession. So I cannot be obsessively measuring the pizza oven all the time. And I need to know in advance, given the initial condition, how cold is outside, and the temperature of the flame, how long should I wait until the oven is ready for a pizza? Um, so how would you try and solve that issue? So you have an oven, You have a temperature gun. What are your steps? Take 2 minutes to talk in pairs or within your group, and then we can discuss it. I'll just run a second to get some markers, which I realize are not here. Okay, so how would you do? I'll point to groups. Your group. Yes. So imagine that you have kids who don't want you to go and check the oven all the time, but you need to be very precise when you put your pizza in. That means you need to figure out a way to know in advance at what point in time the oven will reach, let's say, 400 degrees. Yeah, and you can do all the prep you want, right? Yeah, modeling is one, perhaps a bit obvious answer, but it's a non-trivial answer, right? Yes, you can actually measure it, yes. The outside temperature, yeah, it's a constant. Yes, exactly. Yeah, but you're saying, okay, we measure something, and then we have a black box, which we call a model, and we want it to spit out a timing. This is a non-trivial answer. Thank you. Anybody had some additional points on how to get there? Yes. Mm-hmm. Mm-hmm. Yes. And for some reason, physicists called it the T infinite. That's the temperature of the flame. But yes, yes. It would decrease, right? Yeah, because the difference between the outside, or at least the pizza stone temperature and the flame temperature decreases. Yes. Mm-hmm. Yeah. Uh, Okay. So yeah. So you're saying, okay, we know something about the world. That is, for instance, that there are some important parameters like initial temperature, like the flame temperature, and like the temperature at time t of the pizza stone, because the difference between the object that we want to hit and the temperature of the flame determines how much heat can be exchanged. Right? We also know that there is a specific shape in the heat of the pizza stone, which means that there is a fast increase in heat, which slows down over time. In principle, I guess we could say asymptotically trying to reach the temperature of the flame. Right? It cannot become higher unless there's a Maxwell demon, but we deal without Maxwell demons. Um, good. So what you're saying is we should actually go try to figure out what we already know. Even if there wasn't a literature on thermodynamics, we would start having some constraints and we would need to turn them somehow into a model. And we don't know yet the details, right? Because we're not heat experts yet. Good. Comments on this? Good. So what I did first is, well, first let's look at how the temperature changes in the pizza stone as we measure it. And given this is a real world problem, right, we have three raters, all of them doing the measurements. You can see here the measurements. They're also on Brightspace if you want to play with them. Uh, the x-axis is the measurement time, meaning the first time, the second time, the third time that one of the rater has measured those. The second x-axis is standardized in seconds because the measurements are not super regular. The y-axis is the temperature, and the colors are the three raters. And as I was doing this, I realized that I could actually build the whole of method 3 on these data, because there's repeated measures, there's nonlinearity, there's missing data, there's interquarter reliability, can do lots of stuff. If then we ask people to actually taste the pizza and do Likert scale ratings, that's like 2 semesters of classes, right? But so this is where we start. How, before doing a cognitive modeling course, how would you go at modeling these data? Yes. So this is temperature, big. I know it's confusing, but it's a function of time. And ideally, it's not just a function of time, it's a function of time in a linear space, right? Meaning that we have an initial temperature, that's the intercept, and we have a certain amount of degrees that the temperature is increasing per unit of time. I think that was something that you, maybe Jakob, were discussing during the discussion before, the group discussion. Yes. Good. So this is a linear one. Now you've gone through method 3, so you know that linear given that data is probably not going to get you all the way, you might sort of, like if you cut away the early part, you might get something there, but it's going to have some issues. So what are alternatives to using a linear model? So yeah, Lauritz before mentioned log transformation, right? So you could have a log normal where the log of t would be a function, a linear function of time, right? Does that make sense? That's a very common thing in psychology or cognitive science. You have something that doesn't look quite right. You do a log transformation and hope for the best. Or if you're slightly more sophisticated, you build a log normal or an exponential model that does that for you. Good. Don't want to spend too much time on that. So this is what I did. I have a blue model, which is the linear model. And I have a pink or red model that is the log normal model. So do they look like models that we should trust? Right, there is clearly some issues. For instance, we mentioned before, there is a fast rise in temperature and a slowdown. None of the models capture that. Second, we're probably not going to be very good at predicting what happens after the measurements are done, right? So if this continues, it goes straight up and the temperature is plateauing because it's reaching the effective temperature of the flame. If we, think that the red model is best, like we're going to burn down the world, right, in just a few more minutes. So these tells us that we cannot really use traditional models to describe these kind of data. To be fair, right, we could go to the whiteboard and design a model that would more or less fit the data. Some ideas that I'm throwing out there, right, we could do a sigmoid curve. So we know the temperature of the flame, which means that we could say that between the initial temperature and the temperature of the flame, it's a 0 to 1 space, and then model that using a logistic log odds so that we get this asymptotic behavior, because even if you move up the same length of step in log odd space, if you remember, right, you're moving less and less in probability space, in the 0 to 1 space. So we could get something that somewhat resembles the data as soon as we change the pizza stone or we turn down the gas flame because the gas flask is almost empty or the temperature outside is different. The model fails. We need to do the measurement again in order to get a model that fits the data, right? So we can get a model that describes the data well, but it doesn't generalize to different contexts. Does that make sense? Good. So I'm trying this example for the first time this year, so tell me if it doesn't work. Right. This is what, for instance, in machine learning is called a distributional shift issue. Right? The model can end up performing really well. We can throw a deep convolutional neural network to the data, right? The model will learn the shape of the data, but as soon as we go to data that is different from the one that we use for the training, it's very difficult to generalize. So, luckily for us, there's prior knowledge, right? There's stuff that we know about the word or that we can reconstruct. So there's something that's called the heat or diffusion equation by Joseph Fourier. I don't want to really, nerd you too much in this stuff, but please try to follow, because the idea is that we're learning a process on how we do things. So we have that in that equation, P is the density of the solid, in this case, the baking stone, and C, and what's called the subscript P is the heat capacity of the materials. Pizza stone. You can actually go a very, very deep rabbit hole picking up your pizza stone, right? There's very many different things. T is the temperature, and that delta means the change in temperature at any given time. The T is time, and we use that specific notation, delta T over delta small t, because this is a differential equation, meaning we know that in the world, to a certain extent, changes are continuous, but for an infinitesimal change of time, we want to calculate the change in temperature. So the change in temperature per unit of time, taking into account the density of the pizza stone and the specific heat capacity of the pizza stone, is given by K, which is the thermal conductivity of the material, how fast it acquires heat and shares it with the neighboring material. I can't remember what this is called, but these triangle, yeah, that's the big cap. Yeah, so but it is a specific let's call it delta square, is how the temperature is distributed on the pizza stone. And Q represents the heat generation or input per unit volume. You look at this and you say, what the heck, right? Do we really need to do all this stuff to know how long we should wait until we get to bake the pizza, right? And this is a very important question, right? So when we do models of behaviors in our experiment, when we do models of cognitive processes in a patient population, when we do models of decision making in a company, right, or in a user, right, what's the level of detail that we need? This is something that will come up again and again and again. Luckily, physics has done some of the hard work for us. So we can assume that the pizza stone is a spherical cow, meaning we can assume that the pizza stone is not a body that heats in differential ways according to the closeness to the flame and the conductivity and so on and so forth. We just say the pizza stone is a point in space, and when it hits all at once. And that's basically the lump capacitance model that assumes that the temperature of the pizza stone is homogeneous, which allows us to simplify quite a lot the equation, right? You can see that one is slightly simpler. And we have the T is the stone temperature at any given point in time. Small t is time in seconds. H is the heat transfer coefficient. A is the surface area exposed to the heat. M is the mass of the stone. Seems simpler, right? But still not. Cp is the specific heat capacity. T is the flame temperature, or T infinite. And, right, these again, to me, given the problem I'm trying to solve, is too complex. But luckily, there are some things that do not change as long as I use that specific oven, right? So H, A, M, and Cp, they're constant given the context in which I am. And I can sort of lump together into a constant that I'll call hot. Right? It's a constant given by a bunch of parameters that do not change given the pizza oven. and that determines how quickly the stone heats up for a given differential in temperature. Right. So now we have that equation, and at this point, I felt like I was back in high school. I haven't solved differential equations since, so that's been fun. So we need to figure out how we can solve, if you remember, how we can solve a differential equation for t. So we want to know, how do we determine the temperature at a given time? From high school memory, actually, maybe I should actually do it on the whiteboard. I think it's more fun. So we have the delta T divided delta small t, which is equal hot times temperature of the flame minus the current temperature, right? So if we want to remove the differential stuff, we need to integrate, right? Do an integral of the equation. If you're not following all the details, I know I'm casting you in deep waters, and we will not be solving integrals throughout the course. Do not worry. I just want to showcase the way that we can build very complex models, right? So we can rearrange it. So we can do that, the delta t. So we move these here, and we move these here, because we want to solve for t. So delta t divided T of flame minus the current temperature is equal to hot divided, not divided, sorry, times delta small t. This, if you remember from your basic calculus, which is not that very basic, is basically delta of x divided a constant, whatever the constant is, minus x. You can look up your cheat sheet for integrals, and that has a specific solution. I looked up my cheat sheet for interest. I don't need to remember that stuff by heart, which is minus logarithm of a minus x, that is the temperature of the flame minus the current temperature. That's the integral of that part of the equation. When we look at this, hot is a constant, doesn't change over time. So as we integrate time out of that, it stays the same. And then if we want to integrate the change in time, we multiply by t, and we add a constant, t. Does that make sense? You don't need to follow all the details, right? It's just we're trying to solve this, and I thought it would be fun to do a bit of math. But that's not necessary to follow the rest. So, and if you're interested, like all of these is both in the slides and in the course notes, to which I will give you a link in a few slides, where everything is expanded and explained. Let me see where I am. I'm integrating both sides. And then what we can do is we can solve it, right? We can say that minus the logarithm of, with a natural base of the temperature of the flame minus the temperature at this point in time of the pizza stone is equal to hot times T plus a constant C. We can measure the temperature of the flame. We can measure T. We know that hot is a constant, and we'll figure out how to calculate in a bit. T is something that we know when we measure things, but C is a constant that we don't know, we wouldn't even know how to measure. Luckily, math is our friends, right? What we can say is we can see, what if we solve for C? right? So C is equal to minus ln of T of the flame minus T minus hot times T, right? Thank you. Then we have, well, that simplify things, right? We say we're doing these at time 0. So we actually know how things are. 0, the temperature at T at the beginning is the temperature of the environment. And the temperature of the flame is something that we can measure, right? Which means that C is equal to, and I'm just going to use it here, right? Minus the logarithm of T of the flame minus T of the environment. And the heat transfer hasn't had time to work yet, so we can ignore it, right? Because we are at time 0 just before we turn on the flame, right? Or at the moment we turn on the flame. So we actually have something that we can replace to C. And then, I don't want to bog you down too much, but we can solve it. And we get that the temperature at any given time is equal to the temperature of the flame plus the difference between the initial temperature and the temperature of the flame multiplied by the exponential of minus hot times T. Right? So we have an equation that we can start thinking about. Now you look at that equation and you say, well, there are stuff that we can measure very easily at the beginning. What's the initial temperature? What's the temperature of the flame? What's the initial time? Then the question is there something that we don't know? Is there something that we still need to figure out? Well, we have hot. Hot is something that is very complicated. We put a lot of stuff in that and we don't know it. But that's where the measurements that we just did can help us solving. Because once we have everything else, we can actually solve for hot. And then we have a number that can help us calculate how the temperature should change. And also, I should say, what's my secret for solving all of this? Actually, apart from my high school book cheat sheet, I was sending WhatsApp messages to my mom, who used to be a math teacher. And she was sort of double checking all my calculations on her piece of paper, which is a nice bonding experience. Also, historical fact, apparently Newton solved this already. Should have discovered it before having fun with that. And he called this the law of cooling because when you solve it, you feel very cool. Right. So what we do is, or at least what we learn how to do is we take that equation and we start exploring it, right? We want to understand it. So we fit different parameter values to that equation. Initial temperature, right? From minus 10 to 30, because it's never too cold or too hot to eat a pizza. The flame temperature, these are very low, but there's complicated physical reasons for that. So actually a gas flame is technically 1200 degrees, but the effective temperature that it can give to the pizza stone is closer to 400. Physics, yay. So different flame temperatures and different values for hot, right? We can see that what we get in all these cases with slightly different shapes are curves that follow exactly the behavior that we want, right? So we have not maybe with this very low capacity for heat exchange, But even at 0.02, we get these very high increases early on, which get, slower and slower. And we get that maybe at the beginning, the initial temperature matters, but really it doesn't matter that much the more time we give the flame to work its magic. And when we get to even values that are quite low, like 0.02, right, we get these elbow shapes, meaning that they are assuming that all the heat exchange is going to happen at the very start, right? The heat transfer between the flame and the pizza stone is almost instantaneous. Why are we doing this? Well, because I don't understand equations unless I plot simulations from them, but also because this is giving us kind of a range of realistic values for these parameters, right? We know that going all the way up to 0.02 doesn't give us the behavior that is realistic, which means we already have some prior knowledge on hot, a range of plausible values. Yes, so we measure temperature, T at different times, the initial temperature and the flame temperature, right? And so what we do is we can build at the end of this course a model in Stan, which takes the data, knows that there's a variable called hot that we need to estimate. There is an error. You've seen how much things swings, so we shouldn't forget the error term. We have the equation. That's exactly what we wrote before, right? Average estimated temperature is equal to the temperature of the flame, blah, blah, blah. We have a hot parameter for which we have priors, which we just saw before. We have a sigma parameter for which we have priors, and again, we'll go there. And then here we have a model that is estimating, given the actual temperature that we measured, the mu that we estimate from the equation, and the sigma, how likely different values of sigma and hot are. We'll get there in 3 weeks. You'll be able to do that. We can also do multi-level because there's multiple raters, right? Multiple measurers. We don't need to go there. I just want to give you a sneak peek. We'll do this in about 6 weeks. We could have also built it with BRMS, but because there's a non-linear way of coding in BRMS, escaping the regression work, but I didn't have the time to solve the divergences, so this is how I would have coded it, but it doesn't work. Stan was much easier. We fit the model, and this is how the model works. Right on time for the break. Yay. So you can see my daughter is much better than me at measuring. My son is a boy. He got distracted. Something funny is going on with my measurement, right? And again, right, I think these kind of examples are super fascinating because they give us a very concrete grasp on the problems that we will deal with. When we see this, we need to figure out what's going on, right? In some cases, we'll figure out that something has gone funny with the data collection. Tristan, what can we do with them? But here, there's 2 raters that are supposed to be quite reliable, right? And since you're here in my class, you would have expected me to be right on top of the model. What is going on there, right? Sometimes the model is not good enough. Sometimes we need to understand the data generating process in the collection of the data. What's going on here is that I was measuring at the center of the pizza stone. The pizza stone rotates. The center stays constantly away from the flame. My daughter was measuring the pizza stone close to the flame. And we made an important assumption in the model that we said that as soon as the heat is exchanged between the pizza stone and between the flame and the pizza stone, it instantaneously spread through the whole pizza. She was actually measuring much closer to the model assumption. And it's so beautiful to see it here, right? The model works. We can then use the model to make accurate predictions according to the radar, how long we should wait in minutes playing cards till the oven reaches different temperature. And this one works pretty well. We tested it. And then we get pizza, right? So after the break, we'll discuss why are we even talking about that, and now I'm hungry, right? So let's take 10 minutes break. Let's meet again at 1:10, and we'll solve that issue. Good. So do you have questions so far? I'm sure you have plenty of questions, but do you have specific things that you want to ask before we move forward to why we did this? Okay, so why are we even talking about this? Well, pizza. But the real point is that here we had a relatively well-established physical phenomenon, temperature, which is, we think, as quite simple, right? And even a simple temperature problem requires actually careful thinking and modeling using prior knowledge, or if we didn't have it, trying to develop that knowledge. We need to make meaningful interpretable latent parameters, which are not just a beta, but it's something that we actually know and can do something with in order to make accurate predictions. And while temperature is not as simple as we might think, and there's a beautiful, beautiful book by Hasuk Chang called Inventing Temperature, which is like 400 pages of how early physicists were just wandering in the dark and making idiots of themselves because it's, for instance, oh, we should actually take as the baseline temperature the temperature at any given point of the year in the Parisian catacombs, and that should be how we measure temperature, or very crazy stuff. It took a lot of time and effort to figure out how to measure temperature. However, when we as cognitive scientists, psychologists, educational researchers, what have you, psychiatrists, go and work onto very fluffy concepts like memory, learning, decision making, right? Most of the time, we don't do the hard work. Or actually, to be fair, there's a small branch of psychology called mathematical psychology and a small branch of cognitive science, the most computational aspects that have tried to do this work. There's a lot of work in these directions that is done in experimental design, right? Trying the experimental setup, doing these hard work. Right? If model A is true, condition A should be better. If model B is true, condition B should be better. And then we can do a t-test. But there hasn't been generally a use of these careful model, explicit model building for real world contexts, which can go hand in hand with the experiments. And the course is exactly trying to help you do that, slowly building up ways and tools to computationally formalize cognitive processes, explore the implications of these models, and fit them to real data. Now you're reaching, the end of your academic career. It's like a year and a half left. Not all of you will do research, so you might also wonder, who cares? But actually, these kind of models can be more generally useful, both as a way of thinking. We develop very careful workflows to figure out what the biases of our models are, which applies to anything in machine learning, right? But also, these models tend to be way more precise at giving us the information we want than a traditional regression. So they are used in A/B testing. They are used, or they start being used in clinical practice to, instead of using standardized scores like, oh, you do this reinforcement learning paradigm, and the average man in Denmark from the 80s, when we measure this stuff, we put it at 100, and then we measure how much you deviate from that. But all the trials are there, and we're trying to figure out whether, because that's the promise, using more careful models actually doesn't simply tell us that patient is 10 points below average, but can tell us, and this is due to an attentional dysfunction of this kind, compared to this is due to a problem with working memory, compared to blah, 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 right? Which has actually important implications for the treatment and for the kind of scaffolding activities that you can build for patients. I was just talking with a student of Josh, who has been using it to model data from swaps, right and left for company. It's not Tinder, but you can actually get much more precise information on optimizing the next proposed match if you model more precisely what's going on. Oh, actually, I put these in front, but yes. So we already know stuff about cognitive processes, so why not use it? Why did you study it otherwise? We want to learn more from the data. We want to put these cognitive models of cognitive processes to the test to develop them better. And this course, accordingly, will build on and complement your previous focus on cognitive science. So theories to formalize and design from what you learned before. Experimental design, right? So how can we actually use what we know about cognitive processes to set up the most informative and realistic context for assessing hypotheses? And statistical modeling, because you already understand the laws of probability, Bayesian techniques. You have some ideas on statistical workflows because you took method 3 with me, lucky you. And now we're actually going to develop it into a full-blown thing. Oh, here is kind of a really nice quote that I like to read aloud from a book called Models of the Mind, which is a very discursive history of mostly neurocognitive models of how cognition works, trying to sort of explain the different contributions that mathematics and engineering have given to this model, like Hopfield fields and convolutional neural networks and all these sort of things. But I think it really gives a good idea of why we do formalized models. And it starts, as I do, a bit far away. And it says, the web-weaving spider Cyclosa octotuberculata inhabits several locations in and around Japan, about the size of a fingernail and covered in camouflaging specks of black, white, and brown. This arachnid is a crafty predator. Sitting at the hub of its expertly built web, it waits to feel vibrations in the web's threads that are caused by struggling prey. As soon as the spider senses this movement, it storms off in the direction of the signal, ready to devour its catch. Sometimes prey is more commonly found in one location of the web than others. Smart predators know to keep track of these regularities and exploit them. Certain birds, for example, will recall where food has been abundant recently and return to those areas at a later time. Cyclosa octotuberculata does something similar, but not identical. Rather than remembering the locations that have fared well, that is, rather than storing these locations in its mind and letting them influence its future attention, the spider literally weaves this information into its web. In particular, it uses its legs to tug on the specific silk threads from which prey has recently been detected, making them tighter. The tightened threads are more sensitive to vibrations. They're tighter. Smaller thing will make them vibrate, making future prey easier to detect on them. Making these alterations to its web, Cyclosa octotuberculata offloads some of the burden of cognition to its environment. It expels its current knowledge and memory into a compact yet meaningful physical form, making a mark on the world that can guide its future actions. The interacting system of the spider and its web is smarter than the spider could hope to be on its own. This outsourcing of intellect to the environment is known as extended cognition. When a scientist, mathematician, or engineer, or cognitive scientist writes down an equation, they are expanding their own mental capacity. They are offloading their knowledge of complicated relationships onto symbols on a page. By writing these symbols down, they leave a trail of their thinking for others and for themselves in the future. Cognitive scientists hypothesize that spiders and other small animals rely on extended cognition because their brains are too limited to do all the complex mental tasks required to thrive in their environment. We are no different. Without tools like mathematics, our ability to think and act effectively in the world is severely limited. Mathematics makes us better in some of the same ways written language does. But mathematics goes beyond everyday language because it is a language that, well, here I disagree, but it is a language that can do real work. All languages can do real work. It just works different. The mechanics of mathematics, the rules for rearranging, substituting, and expanding its symbols are not arbitrary. They are a systematic way to export the process of thinking to paper or machines. Alfred Whitehead, a revered 20th century mathematician, has been paraphrased as saying, "The ultimate goal of mathematics is to eliminate any need for intelligent thought." And again, um, some of these things are maybe stretched. All languages are useful. We cannot start doing cognitive models in mathematics, right? We need to start with language, which is very flexible and allows us to communicate in more human-friendly way. But then formalizing these models into equations does something different and complementary. By building computational models of cognition, we change the way we think. These things give us affordances. As I said, one of the things that I had to come to terms with in my academic career is that my high school math only carries me so far, right? When I look at papers with these equations, sometimes my mind goes blank. But what I can do is I can open up my RStudio, my positron, my VS Studio, and I can start coding the equations and plotting what they mean. And then suddenly they make sense, right? So I can actually access, thanks to these different affordances, a very precise way of describing the word. Some of you will look at the equations and go, whoa, that was fantastic. Others will be like me and will need to code them and plot, right? But no matter how we read and use these equations, they give us access to different ways of being precise, different ways of exploring consequences, and so on and so forth. Good. So the idea is that these used so far, this is the word of the generalized linear model, t-test, ANOVA's correlation, GLMs. And here is a universe of wild exploration, fun, bespoke cognitive modeling, right? You can go and start playing. The one thing that I want you to be really aware is that this picture really showcases how humans end up thinking. It's full of boxes again. And if you talk to a lot of the people who do cognitive modeling out there in the world, let alone if you speak to cognitive neuroscientists, my dear colleagues, when you speak about cognitive modeling, they don't hear, the creative process of picking and choosing and building models that fit your theory and problems, but they hear, oh, do you use reinforcement learning algorithm? Or do you use signal detection theory? Or do you use drift diffusion models? Or do you use, a Bayesian model of cognition, right? So specific models that are already out there that can be ideally with a software package fit to your data. And that's not what we're going to do. That's why, and I'll repeat it again and again, in this course, we can go as slow as you want. We can go back and forth on the topics. We can adjust the tempo, because really what I want you to learn is the way of building models. I don't care you coming out of this course knowing the 16 best models in the field. So the course has 3 interrelated aims: learning how to think on specific problems and formalize models of how people learn and make decisions in those contexts. Learning how to code the models to both simulate their implications and assess how well they explain and predict the data. And you'll have to learn, we did a bit of JAGs last semester, right? So you learn a different probabilistic programming language, Stan, because I don't live in the 80s. No, because I find Stan more intuitive. JAGs has its reasons, and it's very good for doing certain things. I think Stan is more flexible. Some people will tell the same about me and say Stan is just this niche thing, what PyMC uses Python. And then you will have Peter Wull, who you probably know, coming in and say Julia is the future, right? But it doesn't matter, because as long as you learn how to program this different way of programming, that's a probabilistic programming language, then you can apply it to whatever language you want. Yes. At the end of the course, you should be able to start thinking about how to use your own theoretical knowledge in cognitive science to build your own models, as well as to robustly evaluate existing models and their applicability. Good. Why are we doing Bayes? Well, as our knowledge on cognitive processes increases, so does the complexity of the cognitive models that are needed to fit those. And as we need to fit more and more complex models, it gets very tedious to have to use specific optimizers and learning new tricks every time that the complexity increases, while a Bayesian framework gives you a general purpose algorithm, the Hamiltonian Monte Carlo Markov chain, which can fit models of arbitrary complexity. You still need to learn tricks, but the general setup works with arbitrarily high complexity. You can technically fit a transformer in Stan, though it's not going to be very fast. Our Bayesian framework provides us good conceptual tools to think through how to build models, understand their implications, validate them, fit them, assess their quality, etc. What we call a Bayesian workflow, which we started in method 3, and we're going to do more explicitly now. Yes, so we can actually reuse what you learned in the previous courses to do the cognitive modeling. So therefore, we structured the portfolio exam to help you reach this. The exam is a way to help you reach these goals and nothing else. In assignment 1, which is, again, we'll discuss the details, but as usual, in portfolio exams, there's submissions during the course, which are recommended, not mandatory. If you want to get feedback, it should be within the course at the weeks that I give you. But even if you don't submit, it doesn't impact your ability to submit at the end, and it's the final submission that counts for the pass or fail. The first assignment, expected in week 3, is to describe and motivate one possible verbal model of how a certain task that will play that tomorrow morning is solved, and provide an algorithmic foundation formalization of it in R. It's helping you to move between verbal and formal models. Assignment 2 in week 7 is build a Bayesian workflow to analyze matching pennies data. Pick 2 algorithms of those that were discussed and prepared for assignment 1. Simulate and visualize data. Build and fit STEM models on those. So you simulate data, you have the algorithm, you produce the data. You fit the model, which means that you start from the data and you see which parameters the model should have. Produce a written report of the setup and the analysis. And this really gives you all the basis into how to analyze data with formal models. If I know how we're going to proceed, we probably won't analyze empirical data at this stage. We'll work on simulated data to see whether the models actually give the parameter values that we set up in the simulation, right? But we'll see how fast we go. Assignment 3, which is about in week 10, it's apply a weighted Bayes model to a new task. So we'll start from a model that's already in the literature. And what you learn how to do is to say, well, my experimental paradigm is actually a bit different. How do I change the model so it actually fits my needs? Final assignment is the alien categorization challenge. Again, we'll go through a game together. And you haven't had social and cultural dynamics with me, so you don't know the task. But you then have to go through this. We will discuss it, and then you will have to sort of sum up what we've done so far. That is to develop a model that would well describe what you think are the cognitive processes underlying this task, and simulate data and make sure that your model works. And as an optional question, you can actually apply it to empirical data. So does this progression make sense? Good. There's going to be some tough times here because it's a big chunk, but we'll get through them together, right? Everything is aimed at you learning. Passing criteria, because I know people worry. You will get an instruction sheet for each assignment, including instructions and a few questions to answer. You will make a GitHub repository with all the code and data that you use. You will make a separate prose answer to the question with relevant plots with a link to the repository, because it really helps you working on your reporting ability, separating the code from the text. And if you do the work, honestly, attempt to answer every question except the optional, of course. Even if you make errors, this is passed. I will give you, at the very least, collective feedback 1 or 2 weeks after the submission. And if there are some things that are marked as problematics in the collective feedback, I expect you to work on those, right? But errors are not per se a fail, right? Because it's the process of learning how to do this. The ongoing deadlines are for you. The only deadline that really matters is the final one. I really appreciate if you work in groups, because I think that that's where learning works best. I also know that I'm not saying this year, I don't know this year, but not in every year all the groups work. So I don't really expect you to work in the study groups that you're top-down handed in. I don't care, right? You can work alone. That's absolutely fine. Still, it's more fun to work in group, right? Questions on this? Good. There's no censor. I'm the one evaluating. I don't care. I also, we'll do a lot of the work. It's not going to be enough, but we'll do a lot of the work in class, and I'll be moving through the groups. So I'd also actually have a good idea of how the group is working, right? Exactly. It's not a problem. So you can have a group of 4 people all submitting the same thing. Not a problem. There's no censor, so we don't need to worry about that specific formality as long as it serves the purpose of the learning, right? Actually, I'm going to skip this, but you can check in the slides later. I asked people that work in the industry to say what cognitive modeling skills are appreciated in their work, and you'll be able to see that. But I want to get to here. So this is the structure of the course. As I planned it, it never ever goes exactly as planned. Today is the introduction. Tomorrow we're going to do the matching pennies game, where you play the game, we discuss it together, and we start formulating these models of what might be going on there. Next week, with my kids here, because it's winter holidays and the university and schools never figure out how to coordinate their holidays, but I will present tools and techniques and examples of how to turn some verbal models into formal models. And during the practical exercise, I think that we will actually implement those things, because